My name is Patel PB. I am working at SGM College Karad, which is a branch of Rate Shikshan Sanstha. Now today we are going to see the topic magnetic material. First we will see the introduction of this topic and few physical quantities which we must know while studying this chapter. We already know about the magnet. Magnet is pair of equal and opposite poles separated by small distance. There are two poles inside the magnet, namely South Pole and North Pole. These poles are slightly situated inside the magnet. The distance between two poles is known as magnetic length. The distance. I will first draw the diagram of the magnet. This is magnet and this is South Pole, North Pole. The distance between two poles is magnetic length. The line passing through these two poles is magnetic axis. A line passing through the center of the magnet and perpendicular to the axis is known as magnetic equator. Also, the magnetic length is smaller than geometrical length. The relation between magnetic length and geometrical length is given by magnetic length is equal to 5/6 geometrical length. For every magnetic dipole, there is a vector quantity associated with. It is directed from S pole to N pole, and it is known as magnetic dipole moment. Magnetic dipole moment. Yeah. For every magnet, there is a vector quantity associated with it. It is directed from S pole to N pole, and it is known as magnetic dipole moment. It is a vector quantity. Also, we will see another few physical quantities. B is magnetic field intensity, magnetic field intensity, which is defined as the magnetic flux per unit area. Magnetic flux per unit area, I upon A, where I is magnetic flux and A is area. Magnetic flux per unit area is magnetic field. Now this is introduction. We already know that when magnet is suspended in air by means of a string, then it remains parallel to the north-south direction. Now, today we are going to see the topic magnetic material. The first point in this topic is torque acting on a magnet torque acting on a magnet in a uniform magnetic field. I will draw the diagram. This is uniform magnetic field, which is represented by B, and I will draw a short magnet here. This is N pole, this is S pole. The distance between two poles is L, which is magnetic length. Vector directed from S pole to N pole is magnetic dipole moment. When the magnet is suspended in uniform magnetic field, then the forces will act on each pole. The force acting on N pole is in the direction of the field, while the force acting on the sub pole is in the opposite direction of the field. These forces are equal in magnitude but opposite in direction. Therefore, these two forces, equal in magnitude, opposite in direction, form a couple or torque. We can say torque. The magnitude of the torque is given by, we know the formula to determine the torque. Torque is equal to 1 force into perpendicular distance between two forces. The force acting on North Pole is given by Qm into P. This is pole strength of the North. This is magnetic field strength. Perpendicular distance between two forces is, if this is P point, then perpendicular distance between two forces is Np. And from figure, Np upon Ns is equal to sin theta. Therefore, Np is equal to Ns sin theta. Ns is magnetic length, which is denoted by L. Then Qm is pole strength into B. Np is Ns sin theta means Ns is L and sin theta. And pole strength into magnetic length. We know that the formula which we have learned in standard 11. Pole strength into magnetic length is magnetic dipole moment. Means small m. Qm into L is m P sin theta. This is the torque acting on a magnet placed in uniform magnetic field. Now, when this magnet rotates in magnetic field, displacement takes place. And when there is displacement takes place, whether it is either linear displacement or angular displacement, work is done. This work is stored as energy. This work is stored as energy. Now we will find potential energy of the magnet. For that I will first magnitude. You first remember the magnitude of the torque is given by formula tau बरोबर mv sin theta, where m is magnetic dipole moment, b is induction of the magnetic field, and theta is angle between induction magnetic field and magnetic dipole moment. As I have earlier stated that when there is displacement, either it is linear or angular displacement, work is done, and this work is stored as potential energy. Now, how this potential energy is determined? Potential energy in magnetic field is determined by integration tau theta d theta. Integration formula. Integration limits 0 to theta, tau theta d theta. And we have already derived the formula tau is equal to mv sin theta. We substitute this formula in this 0 theta, tau theta is mv sin theta, mv sin theta d theta. mv is constant, we can take outside of the integration, mv 0 to theta integration sin theta d theta. And integration of sin theta d theta, we know that it is minus constant. Therefore, final expression is energy. Final expression for energy is minus mv. The value of this integration sin theta d theta is minus cos theta. Therefore, the potential, the expression for potential energy in a magnetic field is given by um is equal to minus mv cos theta. Now we consider three particular cases. Three particular cases and relation between potential energy and angular displacement. I will plot a graph after that. Now, when theta is equal to 0 degree, theta is equal to 0. When theta is equal to 0 degree, we know that cos 0 is equal to 1. Cos 0 is equal to 1. Then, if we substitute this value in this formula, we get um is equal to minus mv. Um is equal to minus mv. From this expression, it is clear that the potential energy of the magnet is minimum when its axis is parallel to the direction of the field. When its axis is parallel to the direction of the field. In this case, magnet is said to be in stable state. Magnet is said to be in stable state. This is case 1. Another case 2. Case 2. When theta is equal to 180 degree. Theta is equal to 180 degree. The value of cos 180 is minus 1. If you substitute the value of cos 180 here, you get potential energy is equal to plus E. From this expression, it is clear that potential energy is maximum when magnet is anti-parallel to the magnetic field. Anti-parallel to the magnetic field. Potential energy is maximum, but in this state, when axis is anti-parallel to the magnetic field, magnet is unstable. Unstable state. Case 3. Case 3, when theta is equal to 0 degree. Sorry, theta is equal to 90 degree. Theta is equal to 90 degree. When theta is equal to 90 degree, cos 90 is equal to 0. Cos 90 is equal to 0. Potential energy also is equal to 0. Anything multiplied by 0 is 0. Therefore, potential energy is 0 when axis of the magnet is perpendicular to the magnetic field. Now, if we plot a graph of these 3 cases, means potential energy along y-axis and angular displacement along x-axis. Here angular displacement, and here potential energy. When theta is equal to 0, potential energy is minus MB here. Here it is minus MB. Here it is plus MB. Then when theta is equal to 180 degree, it is plus MB. And third case, when theta is equal to 90 degree, potential energy is 0. If you plot a graph, here when theta is 90 degree, potential energy becomes 0. And here it is 180 degree. Potential energy becomes plus MB when angle becomes 180. This is graphical representation of potential energy and angular displacement. Now, when magnet is placed in magnetic field, we know that it gets deflected because on both the poles, forces are acting on it, and magnet gets deflected. It makes angle theta with the direction of B. After some time, magnet comes to rest. When it comes to rest, when restoring torque of this suspension fiber becomes equal to the deflecting torque. This formula is given by restoring torque I d2 theta upon d2 square. This is restoring torque. This is deflecting. This is restoring torque I d2 theta upon d2 square, where I is moment of inertia of magnet and d2 theta upon dt square is angular acceleration. Now, we will find another expression for restoring torque. When the magnet is in equilibrium position and if we displace a magnet through angle d theta in opposite direction, if we displace a magnet through angle d theta in opposite direction, then restoring torque is given by, we have already know that the torque is given by tau बरोबर mb sin theta, but we are displacing the magnet in opposite direction, therefore this torque we have to give a minus sign to this. This is restoring torque. T बरोबर minus T is equal to minus mb sin theta. Now equating these two equations, we get I d2 theta upon dt square is equal to minus mb sin theta. When theta is very small, we know that when theta is very small, sin theta is equal to theta. When theta is very small, sin theta is equal to theta. Therefore, we can write I d2 theta upon dt square is equal to sin theta is equal to theta is equal to minus mb theta. Therefore, we can write d2 theta upon dt square is equal to minus mb upon r into theta. This equation is known as angular simple harmonic motion, and this equation is analogous. This equation is analogous to the equation d2x by dt square is equal to minus omega square x. This is where d2x by dt square is linear acceleration, x is linear displacement, this is angular acceleration, this is angular displacement. If we compare these two equations, this equation and this equation, we get omega square is equal to mb upon r. Omega square is equal to mb upon r, means omega is equal to under root mb upon r. Now period is given by T is equal to period of T is equal to 2 pi upon omega. If we substitute the value of omega in this equation, we get T is equal to 2 pi divided by omega. Omega is mb upon r. Then final expression we can write T is equal to 2 pi into I upon mb. This is expression for period of angular acceleration of the bar magnet. Thank you very much.